of weak measurement. Lijian is a professor at Nanjing University. He did his Ph.D. at Oxford University and a postdoc at the Max Planck Institute before joining the faculty at Nanjing. A reminder to everyone, next week's seminar is also at this special early time. We'll be hearing from Alex Ling from the National University of Singapore about his quantum satellites. So, and if you've got questions, please enter them in the chat. And Lijian, maybe if you can break in the middle, if you think there's some natural breakpoints,
sure.
I can let you share any questions. Okay.
Yeah, sure. Yeah.
Excellent. Well, take it away. Thanks a lot.
Thanks. Thanks for the introduction. It's a great pleasure to give this talk. I'm Lijian Zhang from Nanjing University, and today I'm going to talk about some works we had on the precision of the weak measurement. So let's see. So I'm going to talk about the weak measurement and its precision and some practical advantage of weak measurement, and we'll introduce Heisenberg scaling precision of weak measurement using classical resources. And in the end, I'm going to talk about some direct tomography using weak measurement and its application to the characterization of a quantum measurement. So let me start with the introduction about weak measurement. So in quantum mechanics, standard for Neumann measurement is performed by coupling a quantum system and the meter state. The meter state is usually to be a Gaussian state. And if we want to know the state of a quantum system, we couple it to this Gaussian meter state. And after this coupling, we have some joint state between the quantum system and meter state. And the coupling strength is normally large enough, and the uncertainty of the meter state is small, so that in the end, we'll have a meter state either goes to the left or goes to the right. And if it goes to the left, the spin of the quantum system projects onto the -1, and if it goes to the right, the spin of the system goes to +1. So it's a typical example for that is a Stanglash experiment. So you couple the spin of electrons with the direction that it flies through some magnetic field. So if you look at which point the electron ends into some imaging system, you will know its spin there. But after the measurement, the state of the quantum system is completely collapsed. Either goes to -1 or +1. You lose a superposition between +1 and -1. So what is weak measurement? Then weak measurement is still also you couple the quantum system with a meter state. But in this situation, the coupling strength is very small, and the uncertainty of the meter state is large enough. So you cannot really distinguish between the meter state goes to the left or the meter state goes to the right. So because this coupling is weak, so you will not be able to collapse the quantum system completely. You introduce some small disturbance into the quantum system, and also you acquire some information about quantum system. So there's a trade-off between the information you acquired about quantum system and the disturbance you introduced on it. But this way, you will be able to monitor the quantum system without totally collapse it. So it's useful in some kind of a quantum control experiment. So this is already quite interesting. But this is not the end of the story. If after this big coupling, you perform a strong measurement and post-select the quantum system onto another state, collapse it onto another state, which is %F, then depends on the initial state of the quantum system and post-selected state of the quantum system, you may introduce a very large shift in the meter state. So in this situation, instead of a shift of G, you have a shift of G times SW, and SW is given by this equation, and which is called the weak value. So this weak value can be very large because this denominator is given by the inner product between the psi I and psi f and the post-selected state. You may select this to be close to orthogonal, then you can have a very large SW. So it may lie outside the eigenspectrum of this parameter observable S. So that's why this idea, originally proposed by Aharonov, Albert, and Weidmann, the title is called "How can you measure a component of the spin of a spin half particle with a value of 100?" So that's because you can have a very large wake value here. So there are two kinds of situations here. If the coupling parameter G is unknown to us and it's a small coupling parameter, then we can use SW to amplify these small parameters, and which is called the wake value amplification. And if the coupling strength is controlled by us, then we can have a way to measure the wake values, which has some information about psi I and psi f. So I'll focus on the first situation for the first part of the talk, which is parameter G is unknown, and we use a large wake value to amplify this small effect. So before I move forward, I want to give an example for how the wake value amplification is implemented in experiment. So we can consider about this spin system or qubit system is given by the polarization degree freedom of light, and we initialize this qubit by some polarization controlled equipment, and we use a spatial degree freedom of the light as a meter state, and we couple them together through a Sagnac loop. So if the photons goes clockwise, then it couples to the spatial mode. If it goes to the anti-clockwise, it couples to the spatial mode in another way. And these two beams recombine at this polarization beam splitter again. So if we introduce a shift in this mirror, then we can change the coupling between the polarization and the spatial degree freedom of the photons. And after that, we can perform a post-selection of the polarization degree freedom with another halfway plate and some polarization beam splitters again. And after that, if we can use an imaging system to look at the shift of the beam in its spatial degree freedom, and which gives us the wake value. So because we can have a very large wake value, we can amplify a small effect. So this has attracted quite a lot of interest in its application in precision metrology. I think one of the pioneer work was given by Professor Paul Kwiat, and they use these wake value amplifications to observe the spin Hall effect of light. And after that, there's a lot of works along this direction. For example, they use wake value amplification to measure the pico-radius deflections of the beam, or to measure the attosecond delays of the beam. So all these work are very impressive, but if we look at this wake value expression for the wake value again, if we want to have a very large wake value, we need to have a very small value in the denominator. So that means we should have a very small overlap between the initial quantum state and the post-selected quantum state. So that means the post-selection probability is very low. So therefore, the amplification effect comes at the cost of the signal intensity. The overall signal-to-noise ratio is not really improved. So a signal-to-noise ratio is a very important benchmark about the measurement precision, but it's still not the measurement precision. So the question we were trying to ask is, what's a proper way to analyze the precision of the wake measurement, and whether wake measurement really provides improved precision at all. So to answer that question, we should have a proper formalism of the question. So we just formulate these problems in a proper quantum measurement with pre and post selection. So we start with a quantum system, which is a qubit or spin system, and a meter state, which can be any state. And we apply a coupling between them with some interaction Hamiltonians. Then after that, we have some joint state. So if the spin is -1, then we have this meter state be phi minus g, and with spin +1, we have the meter state to be phi plus g. So it's a kind of a joint state, which is generally to be entangled. We perform the system state, so we project onto another qubit state, and after that, we have a post-selected meter state, which is given by just an inner product between this joint state and this post-selected state, which is given by this. And the success probability of post-selection is given by the inner product, mod square of the inner product between ℅(f) and ℅(g). And also now we're trying to say what kind of information we can acquire from this process about the parameter g here. Now, this is a question being studied in quantum metrology. So basically the question is that if we have n copies of a quantum state ℅ g, and we're trying to estimate the parameter g from this ℅ g, which carries some, encodes some information about g. To do that, we need to perform a measurement denoted by a POVM on each copy of this ℅ g. Then after the measurement, we have a probability distribution, which is hopefully conditioned on the parameter g. So it has some information about g. Now we're trying to estimate the g from this probability distribution. And the statistic tells us that no matter what kind of estimator we use to estimate g, the minimum variance we can acquire about g based on the measurement outcome is bounded by this Kramer-Rao bound. Here, F is this kind of a Fisher information, which quantifies the amount of information that the probability distribution PI conditioned on G carries about G. And its exact formalism is given by this expression. So depends on the measurement we perform on the quantum state ℅ g, we may have different probability distributions, and we may have different Fisher informations. So there's a maximum Fisher information we can acquire, which is determined by how well we can resolve between ℅ g and ℅ g plus dg. And this one is called the quantum Fisher information, and it's given by this equation. So we'll see that this quantum Fisher information has some derivatives of ℅ g with respect to g. It's not very surprising, because if this derivative is larger, then it'll be better for us to resolve between ℅ g and ℅ g plus dg. So that's why this quantum Fisher information have the derivatives here. Now, the best resolution between this ℅ g and ℅ g plus dg and this quantum Fisher information is achieved by the optimal measurement we can perform on ℅ g. And for any general measurement, we have the Fisher information is smaller than this quantum Fisher information FQ. But for the single parameter estimation scenario, we can always find the optimal measurement that allows us to achieve this quantum Fisher information and maximize the Fisher information here. So throughout this talk, I focus on to the situation of the single parameter scenario. If we go to the multi-parameter scenario, then the Fisher information becomes a matrix, and it's not necessarily we can always saturate the Kramer-Rao bound. Now we have a proper way to formulate the wake measurement with pre and post selections, and we also have tools to quantify the precision of the quantum measurement. Now we can use them to estimate the precision of the wake measurement. So we start from the beginning of the problem again. So we have a qubit system, we have a meter state, and we couple them together through some interaction Hamiltonians. We have a joint state, which is given by psi g here. Now we perform some post-elections onto this meter state by projecting that onto a post-elected state psi f. And if the post-election is successful with the probability PD here, then we have a post-elected meter state, which is given by phi d, which contains some information about G. And there's another probability, which is 1 minus PD, that this post-election going to fail. And if it fails, we have another meter state, which is phi r. In most of the studies about big measurement, people ignore this failure mode and only look at the successful mode. So if we use the Fisher information to quantify the information that this successfully post-elected meter state carries about G, we have this quantum Fisher information, which is given by QD. But it's not always we have this amount of information, because the post-election succeed with probability PD. So on average, we have PD times QD. That's total Fisher information we can acquire through this post-elected meter state. So this is the Fisher information we achieve with weak value amplifications. And we can also look at the information about G in this failure mode. And we have another amount of information carried in the failure mode, which is given by this QR. And the probability to have that is 1 minus PD. So that's the information in the failure mode. And in the end, we have this PD and 1 minus PD, which also depends on the coupling strength G there. So we can calculate some Fisher information carried between these probability distributions, which is given by this FP here. And we call this is Fisher information in the post-election process. And if we sum these informations all together, then we have the total Fisher information we can acquire from this the whole process that we perform on this joint state. But no matter what we do here, we're just measuring this joint state psi g here. So the upper bound that we can acquire on the Fisher information is given by the quantum Fisher information of this joint state, which is given by this QG. So in the end, what we do with this weak measurement is basically we perform some measurement on this joint state between the quantum system and the meter state. So the upper bound of the Fisher information is given by the quantum Fisher information of this joint state. So that tells us that this post-election does not really increase the information we can acquire about G. It's basically, it's only a way to extract some of the information contained in this joint state about G here. So that answers a question we have been debating about post-election, debating about weak measurement is whether post-election enhance the measurement precision. The answer is negative. Another question we were very interested in is that to compare the precision of weak measurement with conventional strong measurement when using equal amount of resources. And if we do this properly, we also got a result which is negative. So in the ideal situation, we optimize both of the measurement in terms of the precisions, they offer the same precisions there. And in quantum metrology, very important question we want to have is to ask is whether we can beat the standard quantum limit or even achieve the Heisenberg scalings with weak measurement. The answer is yes. I'll show some examples about this one in the second half of the talk. But let's look at this equation first. So it seems that in the ideal situations, weak measurement does not really provides any advantage compared to the conventional measurement. But do remember that is only true if we optimize both of the measurement, and that means we should have this both of the experiment measurement in the ideal situations. But in the practical system, there's nothing really ideal. We always have some experimental imperfections. Then in some practical systems, then we can have some advantages with the weak value amplification. So this has also been studied extensively over the last several years. And it has been shown that for some practical situations with different imperfections, for example, if you have a dynamic noise, which is you have a jitter input state and detectors, or if the whole system has some correlated noise, or if your detector has some finite dynamic range, so it has some saturations, then in these situations, weak measurement can offer you some advantage in terms of precisions. And also another idea here is that if you use the weak measurement, some of the photons are going to survive the post-selection, and you can reuse the photons and send that back into the system. Basically, you kind of increase the usage of the photons. Then in terms of resources, you also achieve some improvement in your precisions here. So today I'm going to focus about this situation, the detector saturation situation. So before we show why this weak measurement can offer you some advantage in terms of detector saturations, I'm going to give the introduction about scenario we're thinking about. It's a Gaussian meter state. It's a measurement in the configuration space. This is to date, most of the weak measurement studied falls into this category. So the meter state is a Gaussian distribution in its position, and we perform a Hamiltonian interaction Hamiltonian here, which couples the spin to the momentum of the meter state. So this P and Q are conjugate variables. In this example, it's momentum and positions. And after coupling, we have this joint state. If the if the qubit spins down, then we have the shift, left shift of the Gaussian meter state. When it spins up, we have a right shift of the meter state, and we perform some post-selections onto the quantum system. The post-selected meter state. So if we study this precision of this scenario properly, then we can see that if we take into account all the contributions of the feature informations, no matter what the coupling strength is, no matter what the pre and post-selected state are, we always achieve the maximum feature information, which is given by the quantum feature information of the joint state. So that means if we take into account all the contribution of the measurement process, then we do not need really to adjust anything. We simply collect all the information. We achieve the maximum feature information we can acquire from the joint state. If we do only return the information in the successful post-select state, as most of the weak value amplification does, then we only acquire this amount of information which is given by the successfully post-select meter state. And a proper calculation shows that even in these situations, if you optimize the measurement process, you can pretty much recover almost all the information given by the joint quantum systems. There are two particular interesting situations here. Is that if the weak value is purely imaginary, then you should use these situations to maximize these feature informations. And we'll see if you choose the post-selection probability properly, then over a range of the post-selection probabilities, you can have almost saturated this bound here. And if the weak value is completely real, and you should use these situations to perform the weak measurement, and it also pretty much recovers all the information you can acquire from the joint state. But there's one advantage of real weak value amplification over imaginary weak value amplification is that it has offers you a better flexibility to adjust the post-selection probability. So it's basically you have the optimal precision over a larger range of the post-selection probabilities here. So have this in mind, we consider about the practical advantage of the weak value amplifications. So normally in an optical measurement, if the system is ideal, then the precision always increases the intensity of the light. But any detector system has a finite dynamic range. So that means it has a saturation threshold. So once the intensity of the light increases beyond this threshold, then you start to lose the response of the detector to the more photons there. So you start to lose the information you can acquire with by increasing the intensity of the light here. Now, if we perform a weak measurement, then we have a reduced number of photons that being detected by the detectors because it's a post-selection probability here. But as I just showed you that if we design the measurement systems properly, we can pretty much maintain the precision of the measurement without losing without sacrifice the fission informations, but with less detected photons here. So it's kind of like that all the photons may have an equal amount of informations. And if your detector has some saturations, you start to lose some of the photons and start to lose some of the informations. But by performing a post-selection in weak measurement, you can squeeze almost all the fission information into a small amount of the photons, and which avoids the saturation with detectors, but without losing any precision of the measurement. So we perform a proof of principle experiment demonstration of this idea. So we use this kind of Sagnac setups, as I showed you at the beginning of the talk. And we consider about a measurement which is intensified CCD camera. And a standard CCD camera has this kind of different response regimes. So if the intensity is low, then you will see the background noise of the detectors. And if it's with the increase of the intensity, we start to have some response of the detector which is linear with respect back to the input photons. And if we keep increasing the intensities, we start to see some saturations here. And for the detector we use in the experiment, we characterize the response of the detector properly. We characterize its background noise. We characterize its linear response of the detectors, and we characterize its saturation response and also some classical noise of the detectors. So overall, we have this response of the detector is given by, if you have ng photons input, what's the probability to have kg counts per pixel here. Then with this response model of the detectors, we can calculate the fission information of the measurement process, also taking into account the short noise of the input laser beam here. Then we can try to compare the measurement precision with predictions from the fission information analysis. To acquire estimation, to quantify the precision of the measurement in the experiment, we should use a proper estimator. So we tried 3 different estimators here. The first one is the maximum likelihood estimator, which is known that can saturate the chimeral bond given by the inverse of the fission information asymptotically. And we also, but it requires very complex reconstructions of the estimations of the from the measurement outcomes. So we also consider about some simple estimators The first one is the center of mass estimator. Basically, we look at the center of the beam profiles without any prior information about how the beam should look like and how the response model of the detectors is. And also we use a split detector model, which basically split the response regions of the CCD cameras into two and look at the difference between the left part and the right part response, the difference between these two different parts. So to use that, we use that to simulate standard split detectors for estimating the deflections of beams. So it turns out that for all three estimators, if the intensity light input light is low, then the precision of the conversion measurement better precisions. It's because that when the intensity light is intensity of the input light is low, then the whole system is dominated by the dark noise of the detectors. So that means we want to have as much photons as possible being detected to have a better signal-noise ratio. But if we keep increasing the the number of input photons, then we start to see some saturations in the conventional measurement. And the weak value amplification, the weak measurement, avoids these saturations. So it keeps increasing the precisions with respect to the increased number of photons. So we have a better precisions with this weak value amplification in the high input intensity regions. And also we have similar result with another two estimators with center of mass estimator and a split detector estimator. But we can see that this maximum likelihood estimator gives a better precision compared to the other two estimators. It's not very surprising because this maximum likelihood estimator takes into account more information about the whole system, about the response model of the detectors, and also about the short noise of the input photons. So it gives us more information about the parameter G as well. So it gives a better precision. So this is already some interesting result, but the power of weak measurement is not only so, because we can actually have a freedom to choose the post-selection probabilities without sacrificing the precisions to a large extent. So that means for different input intensities, we can choose optimal post-selection probabilities, which both avoids the background noise of the detectors and also avoids the saturation of the detectors. So trying to work in the optimal regions of the response region of the detectors with properly chosen probability post-selection probabilities. So overall, we see that with different input intensity light, we can choose different post-selection probabilities and have a optimal precisions for each input intensities. And overall, we can maintain precision which is pretty much dominated by the short noise of the photons. We did not really achieve the short noise limited precision because we still have some dark noise and classical noise with the detectors. We have like 1.2 times the short noise limit. So this means that the measurement with pre and post selections, not necessarily to be a big measurement, allows us to work in the optimal response regions of the detectors and without sacrificing the precision. So we can, if your detector is not perfect, then we can use this ways to overcome most of the detector limitations here. But for this department, we use laser beams as an input state, and we perform pretty much interferometry measurement. So we ended with a coherent state. So the overall precision is given by the short noise of the precision of the input light. So So we cannot beat a classical limit with this scheme. So if we want to beat the classical limit with weak measurement, then we need some measurement that allows us to modify the photon number distributions of the light. So that means we need to perform some measurement involve the couplings with the photon number parameters operators. So this is kind of a measurement in the phase space. We consider about a special situation which we have a initial meter state, which is a coherent state with average photon number given by the alpha square. And we perform a particular interaction Hamiltonian, which is a conditional phase shift. So the effect of this interaction Hamiltonian is that if we have a spin, if the quantum system is spin up, we have a positive phase in the coherent state. If it's spin down, we have a negative phase in the coherent state. And experimental scheme was proposed in 2013 from Steinberg's group, which is given by this kind of a single photon nonlinear experiment. So we input a single photon at a beam splitter, 50-50 beam splitter, and if the photons goes being reflected, it goes into a nonlinear medium together with a laser beam, and introduce a phase shift on this laser beam through this cross-phase modulation. If the photon goes transmits through this beam splitter and goes to the other arm of this Mach-Zehnder interferometer and does not interact with this coherent state. And after that, we combine these two arms at another beam splitter and perform some post-selections onto this single photon state. Then, depends on the successful the post-selections, we may introduce some weak measurement through this whole process. And we perform some feature information calculations for this scheme. And we see that the result is that if we have initial state, which is given by a superposition between +1 and a -1, then the overall quantum feature information we can acquire is like 4 times n squared plus 4n. This n is the number of photons. So basically, we have a Heisenberg scaling in terms of its precisions. Also, we look at the different contributions for this quantum feature information, which is given by this figure. We have the blue part, which is feature information in the post-selected state, and the orange part is given by the failure mode, and this red part is given by the post-selection process. If we sum them together, we almost recover the joint, the quantum feature information of the joint state. And a particularly interesting thing is that when the coupling strength is close to 0, which is normally the parameters regions we work with the experiment because the nonlinearity of optics is very low. And in this situation, we can say pretty much most of the information about the coupling parameter G is carried by this post-selection process. So that means if we work in this weak measurement limit, we only need to look at whether the post-selection on the single photons is successful or not, and without really look at the meter state, which contains a large number of photons, but they do not have a significant contribution to the feature information. So we performed this experiment with Professor Chuanfeng Li's group from University of Science and Technologies in China. So the whole experiment is shown in this figure. So we generate a single photons with a parametric down conversion process, and we send this photon into a Sagnac loop. If the photons goes clockwise, it enters into a photonic crystal fiber with a strong laser beam. If it goes anti-clockwise, because it goes in the different directions with the laser beam, so the interaction is very small. So after these interactions, at the output of the Sagnac loop, we perform a post-selection onto the single photons and look at the coincidences between the heralding photons and success for post-selection onto the single photons. And we only look at the post-selection probability of the single photons without looking at the laser beams. So the laser beams has about 1 million photons, but it just goes across the setups without any measurement on it at all. So the experiment shows that by this measurement, if we look at the precision we acquire on the estimation of G, it scales inversely with the number of photons n here. So it shows that we have a kind of a Heisenberg scaling, which is 1/n precision here. And also, if you calculate the Fisher informations, which also scales like n to the square of with respect to the number of photons here. So it's also confirms that we have a Heisenberg scaling in terms of the precisions. And also the coherent laser beams are normally considered as some classical resources. So in this experiment, we kind of achieve Heisenberg scalings with classical resources. And also we only perform a measurement on the single photons. So this kind of a single photon carries the information from 1 million photons here. And also because, yes?
Paul Kwiat raised his hand to ask a question, so I wanted to give you an opportunity to maybe ask it before you get off this slide.
Great, thanks. Thanks, okay. Elizabeth. So I was just confirming that the thing you're actually measuring here, the thing you're trying to estimate is this coupling, the nonlinear coupling between the classical beam and the single photon beam. Is that right?
That's right. Yeah, that's right. So basically the nonlinearity of this photonic crystal fiber. Yeah.
So if instead of a single photon coming in, you had a weak coherent state coming in, you'd get the same result. Is that true?
You will get a similar results. That's also some calculations we performed there. It's not exactly the same, but pretty much similar with maybe just a constant difference.
I see. Okay, so because you say you're getting Heisenberg scaling with classical resources, but you do have a single photon input, which is a non-classical input. But you say even if you had a weak coherent state, you'd get the same thing.
You will get pretty much a similar result here. Yes.
Yeah. Okay. Thank you.
Yeah. Thanks. Right. So thanks for the comments from Paul, and also that kind of raised me to the next point that we made is that because the single photons and also weak coherent state and coherent state are very robust to loss. For single photons, if you lose a single photon, you just lose everything. If it does not lose, then you have the single photons. And for the coherent state, if you experience some loss, it's still a coherent state. So basically, the whole system can tolerate very high loss in the whole system. So the overall transmission of the system is about 20%. We lose 80% of the photons through all these optics, but we still have this 1/n scalings in the measurement procedures here. So with that, I think I talked about I talked about two weak measurement applications in terms of its applications in measure some weak parameters. Now I'm trying to turn into another application of this weak measurement, which is direct tomography using weak values. So in this situation, if we have this coupling, if we know this coupling strength G, now we're trying to measure the Fisher information, the weak value here, then we will see that the Fisher information contains some information about the pre and post-selected state of psi and psi f. So if there's one of these state is unknown to us, for example, this psi is an unknown state, then by properly chosen this operator A here and this post-selected psi f here, for example, if we choose this A to be a projector onto the eigenstate of the position operator, and the post-selected state is the eigenstate of the momentum state, we substitute these equations into this one. we immediately see that the weak value is proportional to the inner product between x and psi, which is just the amplitude of the wave function in the eigenbasis of x operator. So basically, if we apply these ideas, we can directly extract the information about the wave functions of this unknown initial state with the weak value, with the measured weak values. So this one is called like a direct tomography. It may have some advantages compared to the standard quantum tomography method. It could be simpler in terms of its operational point of view, and also avoids some complex reconstruction algorithms in the standard tomography setups. And this idea can also be extended into the mixed state characterizations with a little bit more complexities. And in this situation, the weak values is given by the direct distribution of this unknown mixed state, which is equivalent to the density matrix of the mixed state. So this idea has been a very successful idea, and also it has been applied to the tomography of quantum process. But if we look at the formalism of these weak values, we see it's kind of a symmetric formalism with respect to the initial and the post-electric state, psi I and psi f. In fact, this weak value and weak measurement ideas was originated from this a time-symmetric description of a quantum system, which is called a two-state vector formalism. It seems like we have an initial state of the quantum system and we have a final state of a quantum system. The initial state evolves forward in time, and the final state evolves backward in time. And in the middle, sometimes we perform a measurement of the observable A here, and the result is given by this weak value. So it's actually symmetric with respect to psi I and psi f here. So that means if we can use this idea to characterize the initial state psi I, and we also can use that idea to characterize final state psi f here. So what is the final state in this weak measurement? It's actually determined by the quantum measurement we performed on a quantum system. And the whole idea is that you may use a retrodictory description of the quantum measurement, which was originally proposed by Lijian's theorem in 2000. And in this idea, a quantum measurement described by its POVM here, and each of these POVM element can be decoupled by equivalent detection efficiency and normalized retrodicted state here. And here, the retrodicted state is the post-electric state in the weak measurement. So if we want to characterize an initial state in the weak measurement, then we can choose the operators A and properly design the final state that allows us to perform a direct tomography of the initial state. And if the post-electric state or the retrodicted state of a quantum measurement is something that we don't know, we can choose a proper initial state and also a measurement operators, and that allows us to have a direct tomography of a quantum detectors here. These are just two different directions, these two-state vector formalisms for the quantum systems. So for this one, we can for the experiment we can have a coupling between a post-electric state and a meter state, and the post-selection is given by the quantum measurement, and after that we'll perform some meter state measurement and extract the weak values, and from this weak value we can directly characterize these post-selections, the measurement quantum detectors that we want to characterize. So there are two different situations. If the POVM is rank 1, so that means the retrodicted state is pure, then it's similar that we characterize a pure initial state. And if it's sorry, it's rank here. If the POVM has a higher rank, that means the retrodicted state is mixed. Then the weak values give a direct distribution of the POVMs. So I should move a little bit faster. So for the experiment, we use a polarization degree freedom of single photons as a quantum system, and we try to characterize a measurement performed on the polarization degree freedom. And the meter state we use is a path degree of freedom of single photons here. We couple them through this interaction Hamiltonians with some wave plates here. And after that, we perform some joint measurement, measurement on the joint state. The measurement on the system is given by this measurement quantum detectors we want to characterize, and the measurement on the meter state is given by these two observables with S1 and S2 here. So we can see different schemes of measurement, and the other is a general POVM, which is symmetric information complete POVMs. Ideally, this POVM is also rank 1, but because the experiment has some imperfections, so in the end, the measurement could be some mixtures in it. And we applied these ideas to characterize both of the measurement. For the projective measurement, we take them as a pure restricted state. And for all 4 sets of projective measurement, we have an experiment result compared to a good agreement between the experiment result and the theoretical predictions. And also the arrows are the theoretical predictions of the projectors, and the dots are the experiment reconstructed state, retrodicted state, and they also have a very high fidelity. I think it was over 99%. And for the symmetric information complete, we treat that as a mixed retrodicted state. So we characterize its direct distributions and reconstruct the retrodicted state from these direct distributions. We also have a very good agreement between the theoretical predictions and the experimental results. So in terms of fidelities, they seem this direct tomography performs well, but we should ask whether what's the precision of this measurement. Actually, over the last several years, there have been a lot of studies on the precisions and accuracies of a direct tomography method. And the result shows that in this direct tomography method, at least for the state tomography, the small coupling strength and a small overlap between the pre and post-selection states, basically a small post-selection probability, lead to large statistical errors, which is not very surprising because if we have a small post-selection probabilities, we always have a larger larger statistical errors here. So the way to overcome these two problem is, for the first one, we should increase the coupling strength G. So instead of working in the weak measurement regions, we should increase coupling strength to a strong measurement region. But do remember that weak value is derived with some first order approximations. So if we increase the coupling strength, we should get rid of these approximations and have some exact expressions for the measurement result and for the relations between the measurement result and the state trying to be characterized. And for the second one, for the detector measurement, we can use a normalization condition of the POVMs, which basically means that a measurement is complete, so that all the measurement operators should sum up to identity. So that means if you have one of the measurement operators, which is almost orthogonal to the initial state, which may have a large statistical fluctuations, you always have some other measurement operators, which is parallel or close to parallel to a pre-selected state, which has a smaller statistic fluctuations. So you should use these informations from the result with smaller statistic fluctuations to correct the result that with larger fluctuations. So overall, we can reduce both of the uncertainties in the estimations, have a better precision here. So we apply these ideas to our results. So here we quantify the precisions or the fluctuations or the uncertainties of the reconstructed POVMs with by the variance of each of the matrix elements of the POVMs, and also we sum the variance of each of the elements of the POVMs together and as a benchmark of the overall uncertainties or precisions of the POVM set. So we see that for the projective measurement, there are some situations that, for example, for this situation, at least one of the projectors is almost orthogonal to the initial state. So it has larger statistical fluctuations and worse precisions. So after the normalization, we increase its precisions and we acquire almost the same precision for all these projective measurements. For the symmetric information complete measurement, POVMs, after the normalization, we also increase these precisions from this blue line to this red line. And also we see that with increasing the coupling strength, we have a better precisions as well. But eventually, if we keep increasing the intensity strength, we should see a minimum in the precisions, and after that, we will have an increase in the errors. But in the experiment, we did not go that far here. So with that, I think I'm going to summarize about the talk. We perform a proper analysis of the precisions of a big measurement and big value amplification. And the result is that the postelection does not really increase the precisions. And ideally, big measurement offers the same precision and with a strong measurement or conventional measurement. But in certain practical situations, it may provide some advantage. Direct tomography using weak values is a very neat idea and may provide some simple ways to characterize quantum systems. But if we want to have a good precision, we need a proper way to handle its precision here. So the results that I mentioned here are in collaborations with some of my colleagues from Nanjing University and from the University of Science and Technologies, and also from Professor Ian Wormsley from Oxford, NMS Data, and George Nee from Warwick, and also Jeff Landin from Ottawa. And with that, I think I'm going to stop here and thank you for your attention. Since it's only 2 days away from the Chinese New Year, I also wish you a happy Chinese New Year. And thank you.
Thank you very much for an excellent talk. I really appreciate it. I've got a few people clapping in the Zoom. So early on, Ophir had a question that we then didn't get back to because it was from early on. Ophir, do you just want to unmute and ask your question?
Yeah, so early on you wrote with the Fisher information, psi of G, and so you took the derivative with respect to the meter. And I just wondered if the states were orthogonal or non-orthogonal, the ones that differ just by a little g, by dg. It's much earlier. It's very no, it's probably
this way.
Yes, here, right.
Here, okay. So here it's this is just a general formalism of a big measurement of Fisher information. So there's no any other assumptions about whether this psi G. It's not really related to big measurement. So here it's just a general quantum state that has some information about G here. It
Right.
could be large or small. Yeah.
Right, and the two states, psi g and psi g plus dg, they are not necessarily orthogonal, right?
No, they are not necessarily orthogonal.
Yeah, that's what. Yes, thanks.
Yeah.
All right, do we have any more questions now? So I had one, I was really interested in the kind of middle part where you were talking about optimizing the weak measurement given your detector non-idealities, noise and saturation.
Right.
Have you considered the potentially using, say, multiple detectors that work in different regimes and splitting your signal among them and optimizing over kind of multiple systems? Would that be something that you could do as as your signal level changes and other things?
That's a good point. So that means basically, so in addition to the adjustment of the intensity of the light, you also have the freedom to choose the detector you use. Really detect. So your point is that basically you can choose different detectors, or you just use all the detectors simultaneously, but send different levels of light into different detectors.
Yeah, that's the idea. And combining things like single photon detection and homodyne detection, and things that have different kinds of scalings. I mean, I think this would be really interesting.
That would be very interesting. So I don't have a clear idea to clear answer to this question, but I think it's going to work. Yeah.
Thanks.
You're welcome.
Anybody else?
I'll make a comment just because you have this particular slide up, and I absolutely agree, of course, that weak measurements can be helpful in cases where you have noise. And I agree that is the all but the lower right picture on this particular slide. But the lower right picture is we're the one who proposed that. In fact, you can also get the
Oh, do we lose Paul?
on all of the photons in principle if you have a lossless system, and then you approach Heisenberg scaling. Although of course you never really have a lossless system. So
that's right. Yeah. Yeah. Indeed, this one was yeah. So I forgot to mention that it was originally proposed by your group. Yeah. I think the USDC people did the first experiment demonstration, or your group. I couldn't remember which one was the first.
They did one, and we're hopefully we finished one now where we have a substantially better enhancement, more because we have a lower loss in the system. And it works well enough. It's probably not it's technologically a bit of a pain to set up. So it may not be the world's most practical way of getting the benefit, but it does help.
Yeah, good to know that. I'm looking forward to your work. Yeah.
All right. Well, if we've got no more questions, Happy New Year. And